Hello, plasma physics students. Let's start our chapter 10, plasma conductivity and diffusion. We will study here these two properties of the plasma, starting with a very simple model, which is the Langevin equation. In this chapter, we'll see then how diffusion and conductivity may affect the plasma properties. There are two main ways of producing mixing and transport in the plasma. One is through diffusion, the other one, conductivity and diffusion, but the other one is through chaotic mixing and turbulence. Of course, that is a much more radical approach to motion, which is based mostly on convection, turbulent convection. But we're not going to describe that here. We start with simple things, diffusion, which is a much slower process, transport process, but a very important one. And we start with this Langevin equation, which is based on the motion of electrons and ions in a cold plasma, weakly ionized. That is, we're considering that the density of charged particles is much smaller than the density of neutral particles. And we're not going to use, therefore, MHD equations now. We'll start with equation of motion for electrons based on equation equation 4.9 of chapter 8 from 4.9. We know that electron mass, electron density times the derivative of the average electron velocity with time is equal to minus density charge, electromagnetic force, plus other forces. You may consider gravity, you may consider pressure gradient, and collisional forces as well. Two collisional terms, AE and SE, that were described in chapter 8. And we here are going to assume that, let's take G equal to the gradient of pressure, AE equal to 0. Okay, that's just for simplification. We're dropping those forces here, and we end up with this form of the motion equation. Okay, so we have some collisional term here as well, involving electrons and neutral particles. Okay, in this model, we're using the collisional term in this simple form here, minus the frequency of collisions with neutral particles, mass of electron, mean velocity of the electrons. What is the role of this form of the collisional term? Well, it's easier for us to understand the role of the collisional term if we drop the electric and magnetic fields. Then we have just the simple equation for the contribution of the collisional term. So if E is equal to B, which is equal to 0, then we have dUE dt equal to minus collisional term E. Okay, this is an easy to solve equation. The solution, it's a linear equation. The solution is this one. It just integrated and you end up with this, right? Okay, so we have initial velocity, and it decays exponentially with time based on this decay rate given by the frequency of collisions. So the collision of electrons with neutral particles will decrease your electron velocity exponentially. Okay. For ions, you have a similar equation. For ions, the Langevin equation will be just this. And the only difference here in the way of writing it is to add this Z term, which is ZE or ZE is the charge of the ion charge. And then you have the rest is just the same. Okay. Usually we take a UI, the velocity, mean velocity of the ions equal to 0 because their mass is much larger than the mass of the electrons. So in comparison, we usually treat the ions as static. And then this is a Lorentz gas. Sometimes we'll use it, sometimes we'll consider the U velocity, the velocity of the ions as well. But if you don't, then you have what is called the Lorentz gas, where only the motions of electrons is important. This Langevin equation, so this is the Langevin equation. Langevin equation for electrons and then for ions. It's fairly used in the study of ionospheric plasmas. It's useful for the propagation of electromagnetic waves in cold plasmas. Especially because of the simplicity of the equation, it's much more easy to interpret what is going on. Let's now consider the linearization of the Langevin equation. Linearized Langevin. Well, let's start with original form. I'm writing the du dt term explicitly here in the laboratory frame with all the terms. No, this is the du dt, right? And the rest is minus E plus UE cross B minus the collisional term. Okay, you can see here that there are two nonlinear terms in this equation. The first one is this, and the second one is this, because you have here a product of the mean velocity of the electrons, and here you have B. If B is not a constant field, then B is a function of space and time as well, and you have a nonlinear term here. So we'll consider that the velocity, mean velocity of the electrons and the gradient is small, or maybe if you have velocity which is perpendicular to the gradient of velocity, like you have in transversal waves, then this can be dropped because of the scalar product, and this is 0. So either because two are small or because one is perpendicular to the other one, you may drop this term. And the second term can be dropped if you consider that that both are small. But actually, B, to write the linearized form, it's better to consider B in this following form. So first we'll drop this, instantly drop this, because or just because either U and UE are small, and their product is much smaller, or because UE is perpendicular to this, like in transversal waves, as I said. Now for B, we'll treat BR. B is a function of position and time, so R is the position, and we'll have a constant background field plus some fluctuation, which we'll call B prime, and this is more fluctuation. Well, then if you use this B into this term, you have minus E plus UE cross B is equal to minus E. You have electric field plus, then you have B is this, so it will be UE cross B0 plus UE cross B prime. Then if you have a small b prime, then this can be dropped. But actually, you may think, well, what if UE is not very small? We may still think about dropping this term if you can prove that this term is much, much smaller than this. Then we will just keep E and forget about this. So let's try to see why this is plausible. If the modulus of this part is much smaller than this, then UE cross B can be dropped. From what? From this equation, right? 2.3 or 3.2, but well, actually, this is strange. Okay, regardless of which one you choose, let's see from 2.3 even, right? From 2.3. Okay, to show that this is the case, then well, 2.3 would become, which becomes E U E, because I'm already dropping this, so I'll keep just this and part of this. So this is the linearized form of the Langevin equation. Sorry, this is collision with neutrals, right? So it's not nu E, it's nu C. This is if we can show that this can be dropped, then the linearized form of this equation is this. This is why is this the case? To show that this can be dropped, let's consider that our fields are given in the form of plane waves. So if E, B prime, and U are proportional to this, plane waves, right? Where you have frequency, angular frequency, and wave vector. So both, all three quantities will be given in the form of plane waves. We have that the time derivatives will be given by this. The derivative with time of one of those quantities will be the same as minus yi omega times the quantity, right? Because if you derive an exponential function, you get the exponential minus e omega times the exponential, right? So the derivative with time is clearly seen as minus I omega times this. And the same for the curl operator. The curl operator can be shown to be equal to this, ik times the quantity. So the curl of the exponential of a complex function is the same as I, which is the square root of minus 1, I times k vector cross product with the exponential function. This is not so immediate to be seen, it's not so easy to be seen, but if you are in doubt, if you are not familiar with this type of representation, you can just write down some components for E. You have kx, ky, kz, r is x, y, and z, and then you compute the curl of this quantity, and you will see that it's the same as just multiplying ik, the cross product of ik with the same exponential. So we can easily show these relations. In this case, from Faraday's law, you know that the curl of E is equal to minus del B del T. Well, using our definition of B, which is given by derivative of B0 minus, then because of the sign, the B prime. Then, well, B0 is, or B0 is a constant, so their time derivative is 0. Then we know that this can be written like this. And the derivative of IB is like this, right? So it's minus derivative, it will be just this. Okay, from here we get this relation. B prime is equal to K cross E over omega. And we can use this one into 3.3. Where is 3.3? 3.3 is this one. So we can use it like here in place of B prime, using 3.7 in 3.3. We get the modulus of UE cross K cross E over omega. This is the relation we want to show. Using dimensional analysis, what we want is the modulus of UE times K over omega times E, much smaller than the modulus of E. Okay, in this case we have UEK over omega, much smaller, divide both sides by the modulus of E, so it's just 1 here. and it means that UE, the modulus of UE, must be much smaller than omega k. If that is the case, then you can drop that term. Okay, so this is the relation. Since omega over k is the phase velocity, the wave phase velocity, which is usually of the order of the speed of light, and this is of the order of speed of light, okay, and this is much smaller than the speed of light, so the nonlinear term can be dropped. What is the nonlinear term? It is this one, right? No, this one. Can be dropped. Next, we'll talk about section 4, direct current conductivity and electromobility. DC conductivity and electron mobility. We'll suppose a homogeneous plasma, weakly ionized, that is, the Lorentz approximation is valid, where only electron motions are interesting. We will suppose that E is constant to make our lives easier and uniform. And then we'll start with zero magnetic field. If B is equal to 0, then the stationary states of equation 2.1 are. So we're going back to this equation 2.1 here. Oh, sorry, where is 2.1 here? So the length of equation, we're dropping the time derivative. So we end up just with this part here. This is 0, so it's minus EE plus the collisional term, which is this. So we can write minus EE minus collisional term UE equal to 0. By definition, we know that the current density, electron current density is, besides, we know that J is by definition equal to minus the electron charge density, electron average velocity. This is the definition of J. Using 4.1 into 4.2, we get J equal to, then you have minus, with minus, it's plus E square and E over nu ME. I just solve for E velocity and then substitute it here to get this expression here. Now, from Ohm's law, we know that J is equal to sigma conductivity times E, right? Then by comparison with 4.3, we have an expression here for the conductivity, for the DC conductivity of an isotropic electron gas, which is, so comparing these two, we have this equal to NE E square and E nu C for this is conductivity so this is not working. Conductivity for an isotropic, because we have B equal to 0. If you have B different from 0, background field will produce anisotropies. So this is for an isotropic plasma. Electron gas. Okay, or plasma. Okay. We can also define a quantity called electron mobility. Electron mobility is given by this expression, the modulus of the velocity, and this is all modulus. It's a scalar quantity given by this. So this is electron mobility. So if you use 4.1 in place of the velocity, if you solve for the velocity and use the velocity, the modulus of this velocity, using 4.1, you get the mobility equal to minus E over this, which may be written using 4.4 as this: conductivity over electron density and electron charge. Here I use 4.4. We'll use these quantities in the following section, so that's why I'm putting them there. Now for section 4.2, we'll talk about an isotropic magnetoplasma. What happens if I add now a magnetic field? In the presence of B, and now consider B a constant background magnetic field, non-zero, and then the plasma will become spatially anisotropic, and the stationary states of the Langevin equation are now, if you take the next form of, where is it? Here. So 4.1 now, it's not 4.1, so stationary states of 2.1 become 2.1, still considering stationary states. We have minus E, and I'll have to add now this term for the magnetic field, minus the collisional term equal to 0. B0 will be constant and uniform. From 4.2, let's see, 4.2, using the definition of J, we have from 4.2, we know that this can be written like this. Then 4.7 will be minus E plus UE cross B plus, so using here with this minus will become plus MUE J over E and E equal to 0. And we can solve it for J. We obtain the simplified generalized Ohm's law, which we had previously derived. I think it was in chapter 9. We derived this form of the generalized Ohm's law. See, it's the equation 9. Chapter 9, equation 5.37. If we consider that collisional effects are negligible, then the collisional frequency goes to 0 and the conductivity goes to infinity. And from 4.9 there, if collisions go to 0, then this conductivity goes to infinity, and from 4.9, let's see, we can divide J by sigma, then this is going to be dropped. We end up just with this equal to 0. So we have E plus UE cross B equal to 0. Now we can just make the cross product with B in both terms. I'll multiply this by B here and also here. Cross B equal to 0. Then we have UE, just move it to the other side, minus E cross B0. But we know that this is perpendicular to B0. It's actually, it may be written like this: U E cross B cross B. The book tells you this: it's equal to E perp B0 square. Now, why is this true? It's just stated in the book. It supposes that you will see that this is actually equal to this: the perpendicular component of the mean electron velocity times the background field square. Now, why is it? Why? Let's try to make a picture here, and maybe this is becoming clear for you, if in case it's not already clear. Suppose your B field is in the vertical direction, and you have velocity field, mean velocity, electron velocity pointing in this direction. Then you have an angle, theta angle here, and you have a plane here. We can decompose the electron velocity into two components. One here and one here. So we have one parallel component and one perpendicular component. The perpendicular component here, we can draw it as a vector, both of them. This is UE perp. Then we're interested in this quantity. So this is UE cross B0. So if you take the cross product between UE and B0, by the right hand rule, or the screw rule, you have coming this way, right? It should be perpendicular to both. So it's like here. You have UE cross B perpendicular to this and perpendicular to this as well. Now, if you take this one and makes the cross product with B, then you're rotating this toward this. The screw will go that way. So here you have, oops, all right. This is UE cross B0 cross B0, right? Oh, that's wrong. E. Okay, it's in this direction. It's parallel to UE, but it's in the opposite sense. That's why you have the minus here. So this this term here is parallel to this, and actually it should be a vector, right? And what is the modulus? The modulus of this will be the modulus of this times the modulus of b squared. That's why you have this. So more precisely, you have the modulus of UE perp. Not so easy to see at first sight. So let's show it step by step. What is the modulus of this? It is the modulus of this times the sine of theta. So it's the projection of UE over that plane. So UE sine, sorry, this is Portuguese. No Portuguese allowed. So let's put sine. Okay, this is equation star. And if you want to compute the modulus of UE cross B0 cross B0, you have the modulus of UE cross B0 times what is this is the definition. By definition, now the modulus of the cross product is the modulus of first term times the modulus of the second term times the sine of the angle between them. So the angle between this and this is actually pi over 2, right? Because of this. The angle here is pi over 2. Okay. Then the sine of pi over 2 is just 1. So we have UE cross B0 times the modulus of B0. Now, for the modulus of this, it's the same formula. It's the modulus of UE times the modulus of B0 times the angle between them. The angle between them is theta. Then you have this. Now, using star, we can have this times this is equal to this. So you have just UE perp times B naught square. Okay, here I used this. Therefore, UE cross B0 cross B0 is equal to minus UE B0 square. Okay, this is the modulus. So it has, this is a vector which has the same properties. It's parallel to this, it's the opposite direction to this, and it has this modulus. Oh, sorry, this modulus. So this is the equality we're looking for. So, okay, using 4.10, where is 4.10? There. In 4.11, so because, yeah, we'll call this E cross B minus E cross B. In 4.11, U E perp is equal to E cross B over B. Oh, sorry, this is not an arrow. This is B square. So you see that in the absence of collisions, the electrons have a drift velocity. This is a drift velocity. You are familiar with the drift velocity from chapter 2. You can check the equations in chapter 2. We had several different definitions of drift velocities there, but they all had this form. So this is a drift velocity perpendicular to both E and B. So if we take the Langevin equations for the ions, we'll end up with the same expression for the ion perpendicular velocity. That means that ions and electrons move together. So they have the same direction, same orientation, and therefore there is no current here. The current associated with this motion, this drift motion, is J equal to 0. Okay. If you do the same for UI perp, you will end up with the same equation. Same as this one, right? Just change E by I. Therefore, there is no current because both ions and electrons are going in the same direction. This is just a drift. When collisions are considered, they affect more ions than electrons, generating a Hall current. So, if collisions are considered in our analysis, then you will have a current because the electrons will drift faster than the ions. So this velocity difference between electrons and ions, although they are both going in the same direction, the electrons are moving much faster. Then you have a current, and this current is called Hall current. It's perpendicular to both B0 and E. Okay, now let's use UE. Let's from 4.2. Where is 4.2? 4.2 here. So I'll write U in terms of J over E n, and I'll do it in 4.9 here. Okay, in place of this. So let's do that. Let's use UE equal to minus J over E and E. That's from 4.2. In 4.9, we get J is equal to sigma E minus sigma J over E and E cross B. If we use B in the Z direction, then we get J equal to sigma E minus sigma J, sorry, this is B, let's put the B first, B0 over E and E, J cross Z. Okay, so let's write this the components of J using this equation, in this particular case of B and the Z direction. First, let's note that J cross Z, you can easily compute this and show that J cross Z is equal to Jy, the Y component of J times X minus the X component of J in the Y direction. Then 4.15, using this in place of J cross Z, will become J equal to this minus this Jy(x) minus Jxy, and we end up with component by component. We have this, I'll write the X component here, minus this is a scalar, we will repeat it here, and Jy in the X direction, so this is Jy. In the Y direction, we have sigma Y component of E, the electric field. Now plus, because I'll do it with this, so here will become plus this Jx. And for Jz, you have just the electric field. There's no component in the second term. Okay, then we can rewrite these expressions using our quantities from chapter 2. We had the electron cyclotron velocity given by this, and we also had the collisional frequency given by this. This is from equation 4.4. So we know this and this, so if we divide this by this, we get B0, sigma 0, and E. Okay, so we can use, you see them here, we can use this in place of this quantity, and Jx will be just sigma Ex minus Ce over C Jy. Jy will be sigma Ey plus omega Ce Jx, and Jz will be sigma 0 Ez. These are the equations for the current in this particular case. 418, 419. Now, we can, so you see that you have Jx here and Jy, Jx. So this is a linear equation for two unknowns and two equations. So we can solve these equations for Jy and Jx. If you do it, you will find this. So solving system 417 and 418 for Jx and Jy. We get Jx equal to collision of frequency square Vc square plus omega Ce square sigma Ex minus Vc omega Ce Vc square plus omega Ce square sigma Ey. I confess that I have not done these calculations to check if it's correct, but I'm believing that it's correct in the book. It's easy to do it. I'm just too lazy to do it, but you can check it if you want. And Jy is Vc, Vc omega Ce Vc square plus Ce square plus Vc square Vc square plus omega Ce square sigma. You see that the good thing about Bittencourt's book is that it shows you most of the derivations that you don't see in other books. So he's very careful with the deduction of all equations. Sometimes some steps are not shown, and I've been showing those steps for you, but usually it's much more complete than most books on plasma physics in terms of the mathematical derivations. Okay, so we have for 2021, let's do it, let's use both equations into, let's just rewrite this set of equations using these components like this. So from 4.19, 420, and 421, we get an equation that can be written in tensor form like this, where this tensor, it's a conductivity tensor, a diode conductivity diode actually, it's given like by this. So this is the conductivity, the DC, direct current conductivity diode. Oh, sorry, that's my DC conductivity diode, where the components are given by sigma perp is this, times sigma 0 sigma h is this. And you have sigma perp, sigma parallel, which is actually sigma 0 which is this. So we could actually have written just sigma 0 here. Okay, you have the three terms present in the tensor here. And if we want to understand what is represented by this equation 422 and how this tensor works, I think it's easier for us to draw a particular case to see what happens with each equation, each quantity. And then for illustration, suppose that you have B0 in, as usually in the Z direction, and we have the electric field given by this. We have a perpendicular component in the X direction and a parallel component in the Z direction. So this is something like this. I have Z here, I have B background field in the Z direction, and I have X and Y. Let's see, well, I could have the electric field here. With both this is E parallel, right? And I have another component here, perpendicular component. Okay, and then we have some angle between E and B. The direction of E cross B would be that way, so this is minus E cross B, this direction. If we take 422, where is 422? Here. 422 will be, I'll just write the components here from 422. We have Jx, Jy, Jz is equal to the conductivity diode, sigma h, sigma perp, 0, 0, 0, sigma parallel, times E, this component is E perp, 0 here, E parallel for the Z direction. Then we have Jx is equal to sigma perp times E perp. Jy is sigma h times E perp. And Jz is sigma parallel E parallel. We'll call it 426 star. Do I have a 426? Yeah, 426. This is 426 star. And you see that the direction in X, the X direction, is the same as the direction of the E perp. So it's perpendicular to B0. Jx is given by this, so it shows that the flow of the electric current in the direction of E perp is controlled by sigma perp. Sigma perp is the perpendicular conductivity, also called the transversal Peterson conductivity. Perpendicular or transversal or Peterson conductivity. So it controls the flow of the electric current in the perpendicular direction, perpendicular to B0. So the y direction is perpendicular to both E, it's perpendicular to E and to B because they're in this plane. So this is actually perpendicular to both. And the flow of J in this direction is governed by sigma h. So flow of J is governed by sigma h. This is perpendicular to both. You see, remember that perpendicular conductivity is the whole conductivity. So how can I say this? Sigma h is the whole conductivity. Perpendicular to E and B. And in the Z direction, you have just a parallel conductivity, which is the same direction of B0 as B0. So you see that the flow of J in this direction is governed by parallel. Sigma parallel equal to sigma is the longitudinal conductivity. It's parallel to B. So this is Peterson. You have whole and longitudinal. Peterson is perpendicular to B. This is perpendicular to B and E, and this is parallel to B. Okay? So the three important types of conductivities that we find in this conductivity tensor. So equations 4.24 to 4.26 show that if the plasma is weakly collisional with frequency of collisions, you see frequency of collisions much smaller than the cyclotron frequency, then you see that both the sigma perp and the sigma whole h will decay, and the electric current flows basically in the parallel direction, because if this is much smaller, this is much smaller than this, so it tends to 0, and the same here because this is square, so this is going to 0 as well, so this will dominate. If you have B0 no background field, then if no background field, then this term, the cyclotron frequency, is 0 because it's proportional to B. So in the absence of background field, this is 0, and then you have this is 0, so it will be equal to sigma 0, and this is 0, and okay, the same here. So we'll have just both here, and then you have an isotropic plasma, so we can know this here. If B0 is equal to 0, then omega CE is equal to 0, and from 424 to 426, you see that this is this, and this is 0. Without background field, the plasma becomes isotropic. Remember, in isotropic plasmas, you have just one type of conductivity. Your conductivity tensor is reduced to a scalar. It can be represented by a scalar conductivity multiplied by the identity matrix. Okay, we have talked about the conductivity diet. There is another diet, which is the mobility diet. Now, from 422, again, 422, J equal SE, right? So J, let's start with this one, SE. And we can employ 4.2 here, 4.2, to write this like this. We have done it already in this class. So just representing J like this. And we solve it for the electron velocity and write it like this. And this can be written like ME, E. This tensor, the S tensor over NE, is called for ME, so ME is minus 1 S. This is the mobility diet. Why the definition of a mobility diet? Well, I don't know. It's just one more quantity that may be useful in some of the exercises in the list, but I'm being honest with you. I have not used the mobility diet in my works, so it's good for you to know that there is a mobility diet, but actually I have not used it. So for me, whatever. Let's move on to section 5. Now we're talking about alternating current conductivity. And electron mobility. Well, let's suppose that the electric field and both the electric field and the velocity field, the electron velocity, are functions of time and space, and they vary in time as this is time, not two, it's time. They vary in time as an exponential function, complex exponential, like you have sine and cosine, so our derivatives in time will be I times omega, okay? From Langevin equation 3.4, the equation, you have minus I omega, so I'm just writing the time derivative as I omega here, and then you have the electron velocity minus E times electric field plus mean electron velocity times, this is the linearized equation, right? Minus the collisional term. And we can write this like this. Okay, Then you have 5.2 compared to 4.7. If you compare this to, where is 4.7? It's far away from here. 4.7 here. Okay, we end up in an equation pretty much like this one. The only difference is that at this time, instead of nu c, now we have nu c minus I omega. You see? Here, this is the only difference we have. So, comparing with 4.7, the only difference is that now you have, in place of this, you have this. So the behavior of the equations is basically the same. So everything we have done for DC conductivity, you can repeat for AC conductivity, but with this change, okay? So the solution of the equation is the same, just changing U E I way for UC, okay? This. If you want to write down the equations for the conductivities, thus 424 and 425/26 becomes, you have the perpendicular conductivity equal to nu c minus I omega square over mu c I omega square plus omega c e square sigma. You have sigma h equal to this. Nu c minus I omega square plus ce. And let me see, this is h. And you have the parallel component, which is also called sigma 0, given by this. Okay, it's something equivalent to this. Okay, you would have this in the denominator, but then you multiply it by the complex conjugate in the denominator and the numerator, then you end up like this, okay? All right, this is 5.5. If you don't have collisions, if nu c is equal to 0, then the components of the conductivity diode for the alternating current becomes then sigma is equal to this. Sigma h is this. And sigma 0 is I and E this. The new system. And we have complex conductivities here and here. This is complex as well because it involves sigma 0. So you have complex conductivities. This means that there is a phase difference between current density and the associated electric field. This is in the book. There is a phase difference between the current density and the electric field. Now, why? So, complex, I'll just state it like in the book, complex conductivity means that there is a phase difference between J and E. This is given, but why? What does this mean? Let's try to understand this with supposing that you have a parallel component for the electric field given by this. Or just write one of the components of the current and you will basically understand why this is given. So I'm writing this from 426 star. 426 star. So I'm writing just this for the, no, I'll write JZ, okay? So for JZ, I need only E parallel. So that's why I have employed E parallel here. So E parallel, suppose E parallel is given like this. You have time dependence of E in this form, which is, you can write it using Euler's formula. It's this, right? So both ways are equivalent. Okay, from 4.26 star, we know that JZ is equal to sigma parallel E parallel, which is actually sigma 0 E parallel. Okay, this is given there. Then this is equal to, let's write the expression for sigma parallel using this. So it's I m e square over m e omega times E parallel, which is this in our example, cosine omega t minus I sine omega t. Okay, and this, since we have I times I here, you can write it like this. M e square m e omega. You have sine of omega t plus I cosine omega t, right? Okay, now you see what is J. JZ, this is JZ. JZ is equal to this. Now the E parallel is given by this. So you see that there is a phase difference between the electric field. You have, of course, some difference in amplitude, but if you check only the phase, they are both waves with the same wave number. But there is a phase difference because this one starts with, if you consider just the real part of this complex complex amplitude, sorry, the complex electric field. So consider just the real part. You have cosine of omega t, and here you have sine of omega t. But sine of omega t is, you have sine of x plus pi over 2 is equal to cosine of x, right? So there is this phase difference. You can write this like a cosine, but with the pi over 2 phase difference between them, right? So there is a phase difference between electric field and current if you are employing complex currents. Okay, that's why the book states this like that. Okay. Well, the next two sections in the book, sections 6 and 7, They deal with the conductivity in the presence of moving ions and plasma as a dielectric medium. So I'll let you read those two sections. Read them. They're fairly easy to follow, and I think I'll just leave them for you. And since this class is already long, it's a very long video, I'll stop here and finish the chapter in the next video. See you.